Okay, my name is Anna Lubiw, and I'm telling you about two algorithms courses today. The first one is 341. How many people have ever looked online and seen this list of questions that you might get at Google if you're ever interviewing there? Have you ever looked? Some of them are kind of fun. They're the kind of things we do in CS 341. So algorithms, problem solving, things that are at the heart of probably every area of computer science. Here's a little example problem I'm showing. Suppose you have a set of people, you know how old they are and what their income is, and you want to know who are the millionaires under 30 years old, or between 20 and 30, let's say. So you're asking essentially for all the dots that are within some rectangle. And that's the kind of thing we might study in CS 341. Now, if you had that only in one dimension, that is, we only had ages, for example, and I wanted the people between 20 and 30 years old, that you probably already know how to do, using sorting and binary search to efficiently get such a set. Okay. So the topics that are covered in this course are some of the basics of algorithm analysis. Why do we not just run test examples, but rather do a theoretical analysis that says how our algorithm behaves as inputs get larger and larger. Some algorithm design techniques, divide and conquer, the greedy technique, dynamic programming. This is one that people who have done programming contests often know about dynamic programming, but the rest of you should too. It's a very handy technique. Then we study some classic algorithms. So these are ones that it's not that you're expected to be able to come up with them, but every computer scientist should have them in their repertoire. And then we look at some problems that we can't seem to find efficient algorithms for, and why this is. So the theory of NP completeness and undecidability. What the course involves is assignments, a small amount of programming. Programming isn't the main point of the course, but there is a little bit of programming, often in a language of your choice, and a test and an exam. And the weights on these, I think, would depend on who's teaching the course. So the prerequisites, I checked this a year ago, and I think it was correct then, so I'm hoping it's correct now. CS 240 and 245, or the equivalent software engineering course, and the discrete math course. And CS students only, I do believe. In the coming terms, I'm teaching it in the winter, both sections of it. In the spring, Timothy Chan is teaching it, and right now Doug Stinson is teaching it. For next fall, it's not clear who will be teaching it yet, but a sample of 3 is people who are all experts in algorithms. Okay, any questions about CS 341? I think it's a required course, so it's not like you're saying, should I or shouldn't I? Okay. On the other hand, this course is the next course on algorithms, so it goes into more depth, and here it is an optional course, so I want to sell you on this one, that this is a great course to take. So it's more advanced algorithms, and maybe one theme would be, what do you do when CS 341 didn't help you for this particular algorithm? You showed that it's a really hard thing to solve. You can't use dynamic programming. What are you going to do? Here's one example, the traveling salesman problem, which maybe some of you have heard about from popular press or from an early CS course. So we have a certain list of cities we want to visit, and the question is, how can you make a tour that visits them all but travels the least distance? So it would be rather stupid to visit New York and then San Francisco and then come back to Boston and so on. We want a tour of the minimum length. Now, this is one of those problems that I was mentioning before, is NP complete. What this means essentially is that the state of the knowledge is that the best way to do this is essentially to try all the possibilities. There's like n factorial possibilities if there's n cities, so this takes way too much time. So in situations like this, what can we do? What do we do when our problem is too hard to solve? We can look at approximation, and there's a rather straightforward way to find a tour that's at most 2 times the best tour. And that's something that you might even see in 341. But what you would not see, and is a topic that might be covered in 466, is that we can get arbitrarily close to the optimum just by putting in more and more and more work. So if we get all the way to exactly the optimum, we're spending exponential time, but we can approach it in a nice way and get better and better approximations. So the topics are, this one I've been talking about is approximation algorithms in the middle of that list, but we'll also talk about randomized algorithms. This appeals to anyone who likes betting. Sometimes with random coin tosses and making bets, you can do better than otherwise. Amortized analysis, which is a kind of averaging technique when you're going to ask many questions and you don't care how bad one is, but just how bad they are on average. Lower bounds and online algorithms. Those are nice too. That's like the difference between packing your suitcase when you have all your items in front of you versus standing at the grocery checkout and those items come down the row one by one and you have to stick them in a bag as they come. That's an online version. And the course requires assignments written only, no programming, and usually a test and an exam, again, depending on who's teaching it. And 341 is a prerequisite for this, CS students only, and in the coming terms, it's usually offered spring and fall, and I'm not sure if there's a plan for that to change in the near future, but for the moment, that's it. In the spring, Alex Lopez-Ortiz will be teaching it, and right now, Teresa Beadle is teaching it. So again, two profs whose area is algorithms are what you get teaching this course. I would like to teach it next fall, but that's not clear yet. Okay, any questions about this one? 466.